Right, here we are with now the sampling and reconstruction technique for sampling. So what you can see in the kit is basically sampling is the process which has been used for converting analog signal into digital. So this is the basic process which has been there. For a sampler, what you require is a multiplier. To one input of the multiplier is the analog signal. The second input to the multiplier is the sampling clock, which is a pulse waveform, right? So what is the first input you have is the function generator, which is used to generate a analog signal. So you have 1 kilohertz sine wave generator which has been shown. So this is one input to our sampler. The second input to the sampler is nothing but the sampling frequency. Now this sampling frequency is generated, you can directly generate it by using a pulse waveform generator, or here the concept which is used is an oscillator with 8 megahertz crystal is being generating the frequency, oscillator frequency from 10 kilohertz to 800 kilohertz, and basically used is 160 kilohertz. There is a frequency divider which is further used, which is dividing the frequency in the range of 400 kilohertz, 200, 100, 80, 50 and 20 kilohertz. So you can select any one of the frequency as your, that is the sampling frequency. The second rule for sampling is nothing but your Nyquist criteria, that is your fs should be greater than or equal to twice kilohertz. Rather Nyquist criteria, it has to be minimum equal to twice kilohertz, and greater is nothing but what you call it as a sampling frequency. So here as you can see is our analog frequency itself is 1 kilohertz, and the carrier here it's very high, that is minimum is nothing but 2k and maximum is 400. So here it is obeying the Nyquist criteria as well as the sampling. Now verification of sampling cannot be done in this particular that is the kit itself, that is your experimental setup. Why? Because the sampling frequency is much higher which has been used over here. You cannot vary here the sampling frequency. If you want to verify, then you can use an external sampling input. Example, if 1 kilohertz is your sinusoidal waveform, you need to apply a sampling frequency which has to be less than 1 kilohertz, that is twice of less than 1 kilohertz. So it has to be 0.5 hertz, that is frequency, 0.5 kilohertz, that is the sampling frequency you need to, that is apply, so that you can verify the sampling theorem itself. Now we'll just see that how sampling takes place. So from here the sampling is being generated at this particular point, you have the sampling frequency which can be observed by. At this point you can observe the analog waveform, that is function generator generating 1 kilohertz. Now where is our sampler? So this is your sampler which has been used. What is the sampler is, you are applying the input frequency, that is analog input, and here it is the sampling clock which has been applied. Once the switch is turned on, that is you can see that it is for external and one is for internal. We are using the internal carrier, that is the pulse waveform as the carrier which has been used, and then you are nothing but going through two concepts. One is the sampler, that is the multiplier, and the second is nothing but the sample and hold output for the reconstruction part. So we'll first see the analog output and then we'll go to the sampled output. So where is your analog? As I showed, this is your analog output. So we'll see this analog output on the CRO. Yes, it is generating the analog signal. So this is your analog. We can measure the frequency and peak to peak value. So frequency peak to peak is 1.8 volt. You can measure the frequency later, or you can see if I change the component, 1 minute. So here you can see the frequency, for example it is channel 1, 1 minute, yes, measure, sorry, so it's channel 1, oh sorry, I turned off the channel. So here it is channel 1, measure channel 1, and the frequency you can see is exactly 1.00 kilohertz which has been generated, right? So now you have the sampling clock. So what we'll be doing is we'll connecting the second probe of the CRO to the sampling point, and that sampling point is nothing but we are going to connect it at the point, that is the internal generation of sampling clock. So you have here the internal generation of sampling clock. Now we'll see the CRO will set it to auto set. Yes, this is the sampling frequency, a pulse waveform which was generated. You can see that is, this is your pulse waveform. I am varying the frequency by the switch which has been over here. You can see the variation. Now the frequency set is 100 kilohertz. I can vary the frequency from max to minimum. You can see the variation. So first is low component, now it goes on increasing. The high frequency component, that is, as I said, up to 200 kilohertz is the, 400 kilohertz is the sampling clock which is selected. Now I am selecting 100 kilohertz as the sampling frequency over here, so that better waveforms can be observed, right? Now what are the connections further which we are going to go through is, now you need to apply the analog as the input to this particular sampling clock, right? But I'll keep the analog as it is, and I'll just connect now the sampling, that is the analog input, as an input to the sampler. So where are we connecting it? We are connecting at a point, that is the sampler input. Now what I'll observe is the sampled output. Which is the point? This is the point, that is the sampled output can be seen. So I'll just see the sampled output with respect to whom? With respect to analog. So I'll just connect again the analog and the sampled output. We have already seen the, that is the analog and the that is a sampling frequency. Now you can see here is the flat top sampled output, the natural sampled output. But what you can observe here is the sampled output can be seen in both the half. So we call this as a bipolar sampled output. Why? The polarity of the sampled output is positive as well as negative. Usually we use a single polarity for, that is the transmission purpose. So sometimes you cannot see this particular, that is the lower half. We have the sampled output only in the upper half of the part itself. But here it is a double polarity, that is the sampled output which can be seen by. So this is your sampled output. What you need to measure is the peak to peak value of the sampled output. You can have from peak positive or and the peak negative output which can be, that is noted down. So this is your sampled output. Now what is the sampled output? Now we are going to go for the reconstruction part. What is the reconstruction is, the first the signal is passed through the sample and hold circuit. Sample and hold circuit output will be passed now through a low pass filter. Now here there are two low pass filters which are provided. One is a second order low pass filter, the second is the fourth low pass filter. You just now remember that we'll use a simple second order low pass filter, right? So what is the connection for this is, again I have the sampled output, that is the sample and hold output, which will be passed just through the low pass filter. So I have just connected the sampled output through the low pass filter input, and now what we'll be doing is we'll be observing both the outputs together. Before that, we'll see the sampled output and the sample and hold output together on the DA. So and just see what are the variations which you can see for, right? So what you have is once again auto set. So you can see that the sample and hold output and the sampled output, that is second channel you have sampled output, the first channel is sample and hold output. What we'll compare is, see here, the sample and hold output will be matching with the sample and hold output, yes, here. So you can see that the edges which are going to be matching with the positive edge till positive edge of the next sample, the signal is being holded. Again from the positive edge to the next positive edge, the signal is sample, that is holded. So it is sample at the sampling instant, holding till the next instant which has been there. Till what? Till the next sampling instant. So as I said, sample at this instant and hold till the next sampling instant. This is what is sample and hold output. Now same sample and hold output passed through the low pass filter. So what we have done is the connection for sample and hold output passed through the low pass filter given as an input, and this is your output, that is the low pass filter output. Now we'll observe the original signal and the sample and hold output together on the DSO. So I am connecting low pass filter output and I am connecting the original analog signal together. See here, it's auto, that is you can see both the signals are same, that is the constructed and the transmitted and the reconstructed both are same. You may see a delay between two, and that delay is due to whom? That is the low pass filter. The low pass filter charging and discharging may create a delay, and that is what is the delay which you can see between the two waveforms. Otherwise the frequency of the transmitted and the reconstructed is one and the same. So this is your sampling process which has been done. Now if you want to go for the verification of the sampling theorem, we need to, as I said, reduce the sampling frequency in such a way that it is very much lesser than the analog signal, and in time domain what you can see is the transmitted signal and the received signal. Transmitted will have a high frequency component and the reconstructed will have a low frequency component. This is called as downward frequency translation, which is called as aliasing, and then we say that the sampling has not been verified, that is Fs has become very much less than twice of the analog frequency component. So time domain aliasing is nothing but what you call it as verification of sampling theorem. Thank you.